Welcome to week 11. This week we will cover chapter 8, confidence interval. Thank you for submitting your exam 2 yesterday. Now we're starting our very last unit in Math 245. Starting today, chapter 8, 9, 10, and a little bit of chapter 13, those will be on your final exam. And I call it final exam, but it's really just exam 3 because we're not putting Unit 1 or Unit 2 material. The final is not going to be cumulative. I already have your exam for the descriptive statistics unit. That's the one that we took in at school. And the one that you took in my labs yesterday, since we had to go online, was on probability distribution, and sampling distribution. And the very last unit, now we're finally talking about inferential statistics. And the first one that we're going over this week is confidence interval. Chapter 8 has 4 sections that I want to go over. The first one is more like an introductory. We're talking about point and interval estimate a population parameter. The second one and third one, we will actually construct confidence interval to estimate population proportion and population mean. And the last section, we will talk about choosing the sample size for a study. So these are the 4 lessons that we will go over this week. The homework for chapter 8 is open on my labs. I divided it into part 1 and part 2, so that's open for you. And I'm going to have a short Canvas quiz for you to take. It's just like a, because we won't be able to have another data assignment until we go more into chapter 9. So, but I still wanted to do something other than my labs assignment. All right, so let's get started on 8.1 first in this video, and we will come back and do more problems that you will see on the homework on 8.2, 8.3, and 8.4. So this is a little introduction to confidence interval or inferential statistics. All right. When we collect information about a sample, usually the samples are smaller, right, than the actual population, but we hope that sample is a good representation of the population. We often ask the question, when that information can be generalized to the population, is the sample proportion the same as the population proportion? Is the sample mean, median, and standard deviation a good approximation of the population mean, median, and standard deviation? Because that's what we want, right? It will be great if we can do study everybody in the population, but that will be too time consuming, that will be too expensive. So when we take a small sample, a random sample, that will be good representation of the population. We hope that the statistics that we find on these samples are going to be a good approximation of the actual numbers in the population. So, making this type of jump or approximation from the sample to the population is called making an inference. So chapter 8, 9, 10 are all about making statistical inferences, okay? All right, so there are 2 types of statistical inference methods. The first one that we're going to look at in this chapter is making an estimation of population parameters. And in chapter 10, we're going to conduct some hypothesis test. The second one is testing hypothesis about the parameter values. They're called significance tests, and we'll go over them next Friday. In this chapter, we will study the first method, estimation of the population parameter. So when we're making an estimation about the population parameter, there are 2 types of estimate. The first one is called point estimate, and the second one is called an interval estimate. First, the point estimate is a single number that is our best guess for the parameter. So you just guess a single number, and we just call that number point estimate. What's used more often is the interval estimate. It's an interval of numbers that believed to contain the actual value of the parameter. So if point estimate is just our best guess, I think tomorrow's weather is going to be exactly 78 degrees, let's say that. Well, that's a good guess, I guess. But interval estimate, if I say something like, I am 95% confident that tomorrow's average temperature will be in between 60 degrees to 90 degrees, that's an interval estimate. So for example, another example right here, one general social survey asked, do you believe in hell? From the sample data, the point estimate for the population of adult Americans who would respond yes equals 0.73. That's more than 7 of 10. The adjective point in point estimate refers to using a single number or point as the parameter estimate. But then the thing is, if you're just using one single number, what if it is instead of 0.73? What if it is 0.74? We'll say that's pretty close. But another measure, let's look at an interval estimate. The interval estimate found with the method introduced in this section predicts that the proportion of adult Americans who believe in hell falls between 0.71 and 0.75. So, if point estimate is just our single best guess number, interval will be like a little net that we will be able to capture the actual population parameter. Okay, let's take a look at figure 8.1. Here's a picture of point estimate. We are thinking that single number is likely going to be 0.73. But what the interval estimate does is it gives us an interval. We're thinking from anywhere from 0.71 to 0.75. So an interval estimate is an interval of numbers that are believable values for the parameter. So if we get something like 0.74, we'll say, that's believable, but it's unlikely that we'll get something like 0.80 or 0.70 that are not within this interval estimate. So the question is, why is a point estimate alone not sufficiently informative? Why are we going to use interval estimate instead of just point estimate in this chapter? So point estimate by itself is not going to be sufficient because it doesn't tell us how close the estimate is likely to be to the parameter. If you just know 0.73 and the actual parameter say that, what if that is like 0.75? Were you going to say that, oh, we had a pretty good guess, or were we just not even close? Interval estimate tells us that the point estimate of 0.73 falls within a margin of error of 0.02 of the actual population proportion. And by incorporating this thing called margin of error that we're going to look at in this chapter, the interval estimate helps us gauge the accuracy of the point estimate. Okay? So let's talk about a couple of things about point estimator, because we will need to find the point estimate in order to create an interval. A good estimator has a sampling distribution that is centered at the parameter that it's trying to estimate. An estimate with this property is unbiased. Remember how we use sample mean to estimate population mean. Now, once you write down these symbols on your notes, sample mean, we use X with the bar on top. We call it X bar. That is an unbiased estimator of the population mean. And for the population mean, we use the symbol mu. Okay? So whenever you want to estimate the population mean, we're going to find the sample mean and call that the point estimator. Now, if you want to estimate the population proportion, P, well, then it makes sense to find the sample proportion. And that symbol right there is P with a little triangular hat on top of it, and we call that P hat. So sample proportion P hat is an unbiased estimator of the population proportion, P. So those are the two statistics that we're going to use to estimate the population parameters in Chapter 8. In 8.2, we'll look at sample proportion and population proportion. And in 8.3, we're going to do sample mean to estimate population mean. And 8.4 is about finding the sample size that will be best for us. All right. The second property of point estimator, a good estimator has a small standard deviation compared to other estimators. This tells us the estimator tends to fall closer than other estimates of the parameter. For example, sample mean has a smaller standard deviation than the sample median when estimating the center of a normal distribution. So that's why when we are estimating the population mean, we're going to use sample mean instead of median. I mean, they're called the same things instead of sample and population. So you kind of know that we're going to be using the same thing called in the sample. All right. So when we create the interval, that what we're hoping is that the true population parameter is captured in that interval. That's what we hope. Interval estimate is an interval of numbers from one number to another number that is believed to contain the actual value of the parameter. We'll talk about something called confidence level. Things like we are 95% confident or 99% confident. But we'll also talk about as we go higher on that confidence level, our confidence interval will be a little bit wider. I think I have a good cartoon to explain that. I don't know if you can read this one because I think I better find a better quality cartoon than this because it's hard to read. Well, let's read this. Taking a look at tomorrow's weather, the high temperature will be between 40 below zero and 200 above. How confident is this little cat about his confidence interval? Oh, like 100%. High temperature will be in between 40 below zero and 200 above. This guy's never wrong. Oh, that's actually from the TV. It's not from the cat. So it's a cat thinking, oh, this guy's never wrong. Well, okay, but would you call that a good confidence interval though? That confidence interval that this TV guy just used has crazy big margin of error, right? Anything in between negative 40 to 200. See, so when we're looking at confidence interval, confidence level isn't like to be able to say I am 100% confident or 99% confident. That's not going to be the only thing that we're going to care about. We want to make sure that we have a reasonable margin of error because, this information isn't going to help any. Maybe I want to hear something more like the high temperature will be in between 85s and 90s tomorrow. That will help me to prepare an outfit for the next day slightly better than like this kind of information. So we want to contain the actual value of the parameter. Yes, we're right, but we also want to make sure that the margin of error is not too crazy big. All right. So that's the part about the margin of error. I do want you to keep that in your notes. It's one of the key words that we're going to use in chapter 9. An interval estimate is more useful if it incorporates a margin of error which help us to gauge the accuracy of the point estimate. The most informative estimation method constructs an interval of numbers is called confidence interval, within which the unknown parameter value is believed to fall. So say that we have a confidence interval that goes from 90% to 95%. What we hope is that the true population proportion is, suppose that it is 93%, that our confidence interval will be able to capture that in this little net. Okay? All right, number 2 or 3. A confidence interval is an interval containing the most believable values for a parameter. The probability that this method produces an interval that contains the parameter is called the confidence level. And we're going to be given a couple confidence levels to create some of the most basic confidence interval in 8.1, just using the standard normal table. But the most common one that we're going to see is 95% confidence interval. This number is chosen to be close to 1, most commonly 0.95. It will be like us saying we are 95% certain that the mean is in between these two numbers, or the proportion is in between these two numbers. 95 is pretty standard. We don't really use 68% confidence interval because that's too low. Sometimes I've seen 99 or 98, but usually it's going to be 95% confidence interval, confidence level, okay? In this chapter, we will learn how to find the confidence interval, which is an interval where the parameter is most likely located. So why do we depend on confidence interval? When estimating a proportion, we saw that the sampling distribution of sample proportion gives the possible values for the sample proportion and their probabilities, right? That's what we looked at in chapter 7. 7.1, we looked at sampling distribution of sample proportions. And when the sample size was large enough, take a look, well, the sampling distribution of a sample proportion was approximately normal, right? For large random sample, where we multiply n times p, and that came out to be greater than or equal to 15, and that n times p were called number of successes, right? And the other guy, the number of failures, and n times 1 minus p, or n times q, that also had to be greater than or equal to 15 for us to assume the sampling distribution of a sample proportion to be approximately normal. For large random samples, the central limit theorem tells us that the sampling distribution of the sample proportion is approximately normal. And remember, once you identify your NP, and then using those NMP, found the mean and the standard deviation, we were able to use the normal calculator on our StatCrunch to calculate some probabilities, right? So that's going to be useful. When estimating a proportion, well, we saw it also has mean equal to the population proportion. So sampling distribution of sample proportion has the same mean as the population proportion P. But remember, the standard deviation had a bigger formula, and that formula that you used already many times is square root of P times 1 minus P, and we divided that by the sample size of N. Okay, so kind of review of what we did in chapter 7. Since the sampling distribution of the sample proportion is normal, we use the normal distribution to determine how far away we can move from the mean. What z-score we can go up to or down to. So the first confidence interval that we're going to look at is the confidence interval of proportions. So for that one, we're going to use z-score, and for that one, we're going to use the normal distribution. We say we want 95% confidence level. It means we want to make sure that 95% of the population will fall in the interval we pick. Okay, with probability 0.95, and you've heard that number before. Remember the empirical rule, 68, 95, 99.7% rule, remember? So which one had 95% in the middle? It was that 2 standard deviation away point, right? The sample proportion falls within about 1.96 standard deviations of the population proportion. So if you round that up, that's going to be close to 2, and well, to the negative side, that will be -2. But like we said, 95% is pretty standard for confidence interval. So it's probably good to memorize that 1.96 is going to be the standard deviation that we will use pretty often to construct a 95% confidence interval. Okay? The distance of 1.96 standard deviation is called the margin of error. Now let's look at 4 quick examples, and this is up to you. You can either use the table of standard normal probabilities that are attached on page 5 and 6 to find the z-scores, or if you just want to use the StatCrunch to look up the z-scores, we can do that too. But you gotta use one of these methods to look up the z-scores now, okay? Let's look at 4 examples on, I think, page 4. Example, use the z-score table to determine the z-score interval around the mean that contains the following percentage of the sample data. Now, for number 1, what I want is 80% of the data. This means 80% confidence level, okay? Now, where do we want that 80% of the data? I got a little picture for you to look at. It'll be a good idea to copy down this picture. If we want 80% confidence interval, we want that 80% in the middle. So take a look. That's the blue area that I shaded is the 80% in the middle, okay? If you have 80% in the middle, then what you're gonna have to know is, now take a look. If you have 80 in the middle, you will do 100 minus 80 to figure out how much you have to the right of it and to the left of it. 100 minus 80 is 20, right? So if you split the 20 in equal pieces, you will get that you have 10% to the right and 10% to the left. If you add 10 plus 80 plus 10, you will get 100 total, right? Now, why do we have to split this? Because remember that Z table, the table method that we use, they find the cumulative area to the left of it. So I want you to kind of divide up your curve first. And to look for the middle 80%, you need to find the 90th percentile. I mean, we can do that, but what I can also do is I can find the 10th percentile. I can look at the z-score over here, right here. And that number will just be the negative of the 90th percentile, because remember, this normal distribution is perfectly symmetrical. The confidence intervals that we're gonna find in this section 8.1, they're just gonna have same number but different signs, just because in this z-score which is perfectly symmetrical with the mean at 0, we're gonna have, if let's say if that z is 2.3, this side will be negative 2.3. So let's find it. Now you know you want to look up the 10th percentile on the z-score, and 10th percentile is having 10% to the left of it. So what you want to find is the z-score that has 0.1000, or the closest number, closest cumulative area. The one that I found, and this is what I screenshotted, was 0.1003. This number was the closest to 0.1000. So what I read was that the z-score is negative 1.28. So that's one method you can use using the table that I attached on page 5 and 6. Or this is what you can type in. You know that the mean of a standard normal distribution is 0, and the standard deviation is 1. What I should have done is, when I did on the next couple examples, type in 0.10 in this blank and leave this box empty, and then hit compute. They're going to give you that the z-score is negative 1.28155516. It's just more accurate than what I got over here by reading the table, but you see they're approximately the same thing, negative 1.28, and if I round that, that's going to be negative 1.28. It's up to you, whichever method you use, as long as you find the z-score. Therefore, the 80% confidence interval is from negative 1.28 to positive 1.28. And the reason these numbers are exactly the same except for the sign is just because the normal distribution that we looked at, the standard normal, has a mean of 0. So to the right side, to the left side, is going to be perfectly symmetrical with the different signs. But we will look at confidence interval with different numbers. So don't just assume that just because you have negative 1.28 here, that you're going to have positive 1.28 for the other bound. just for this unit where we are using the normal distribution. It will work. All right, let's look at another one. How about we want to find 68% confidence level? Well, you've seen that number before, right? You know that in a normal distribution, 68% of the data are within one standard deviation from the mean. So without really doing the z-score calculation, you know the confidence interval is going to be from -1 to +1. But let's actually find it. Look, if we want 68% confidence interval, we want to stick that 68% in the middle. So if I want to find how much is to the right and how much is to the left of that, the leftover, I'm going to do 100 minus 68 and get 32. These two white sections together have 32%. So if you take half of 32, which is 16, I know there is 16% to the left and 16% to the right. So for me, it's easier to just look up the 16th percentile on the z-score table because that will just be the negative number. And we know that's going to be very close to -1 by the empirical rule, right? So let's take a look. So this is what I did. I just used StatCrunch. Type in the mean is 0 and standard deviation is 1. And put 0.16 after the equal sign, but leave this blank. Notice that the number they gave us, that the z-score is -0.99. And if you round that up, that's -1, right? So to the left, it's going to be -1. To the right, the upper bound will be +1, and that's the rounded confidence interval. Let's do 2 more. I think you're getting this. Okay, what about if you want 95% confidence interval? Now, again, you know the answer already by the empirical rule. We know that in a normal distribution, 95% of the data are within 2 standard deviations from the mean. So the confidence interval that we're expecting is absolutely just from -2 to +2. But let's look that up. If you have 95% in the middle, and I think this is a great point that we need to keep on talking about before we go and do other confidence interval. When we do confidence interval, we want that 95% to be in the middle. So how much are we going to have to the right of it and to the left of it? Subtract 100 minus 95, you get 5, right? So to the right and to the left together, you have 5% of the area. And half of 5 is 2.5. So what you know is that we have 2.5% to the left and 2.5% to the right. Now, what you have to be careful is convert that 2.5% into decimal. What is 2.5 in decimal? And this is what I typed in. Take a look. And in my first 2 examples, I actually just screenshotted the page that showed the answer and everything. But this is what I type in, and this is what you should type in. Type in that the mean is 0, as you know, and the standard deviation is 1. And the other side of this area, and make sure the symbol is less than or equal to, because we're finding the cumulative area, or the z-score that has the cumulative area of 2.5%. Type in 0.025 on the other side of this equal sign, and once you hit compute, it's going to give you that the z-score is -1.959964. Now, if you do some rounding, that will be -2, right? But again, remember I told you to kind of, see this number and kind of remember that number. That 1.96 is going to be the popular z-score number that we're going to multiply. Well, we'll talk about that part in 8.2. But that 1.96 is going to be the popular number that you're going to use to calculate 95% confidence interval for same of the population proportion. So here we go. The 95% confidence interval is from -1.96 to +1.96. Okay? All right, let's do the very last one. What about 99% confidence level? Well, what does that mean? That means we have 99% of the data in the middle of this graph. So if you subtract 100 minus 99, you know that to the right of it and to the left of it together, they have 1%. And half of 1% is 0.5%, right? So what we know is that we got 0.5% to the left and 0.5% to the right. But be careful, do not type in 0.5 for the probability. 0.5% in decimal is 0.005. So when you use the StatCrunch normal calculator to find the z-score, make sure you type in 0.005 instead of 0.5, because 0.5 will be assuming 50% of the data. And what number will you get for the z-score? Which z-score has 50% of the data to the left of it? 0, right? Okay. If you hit compute, you will get the z-score, the corresponding z-score, to be negative 2.5758. And if you round this up, you will get negative 2.58. And because normal distribution is perfectly symmetrical, if that's the left bound, you know the upper bound is going to be positive 2.58. Now, we did it together. We did it actually like using StatCrunch. But here's what I found. Is that Statistics for Dummies cheat sheet. I mean, when I was in school studying the statistics for the first time, I remember my professor, she made me memorize these critical z-scores. The critical values, these z-star values, are an important component of confidence interval that we'll be using. And if you are good at, well, for our class, you know, right now, these information is out there. So you know how to find it using StatCrunch or using the normal distribution, the standard normal table. But if you're interested in finding the confidence interval like 95%, that critical value that you're going to use is 1.96. That's the one that we found. We also find that 2.58 for the 99%. What else did we find? Did we find this 1.28 for 80% too? But these are kind of, somebody who does confidence interval often, very often, you get used to these numbers because we keep on using these numbers. But this isn't any information that's hidden from anybody. If you just want to kind of look up these z-star values, that's okay. But just gotta know that we are gonna be using these numbers to construct confidence interval in section 8.2. Okay, so that is it for 8.1. Just kind of an introductory. You know what a confidence interval is. You know it is involving two different numbers to the left and to the right. And but we didn't really construct one that to capture the population proportion or population mean just yet. So 8.1 was just talking about, hey, point estimate, interval estimate. Those are the two different things that we can use to estimate the population parameter. But I think that was something important for us to talk about. So please come back and we will work on constructing confidence interval to estimate population proportion in the second video. Okay?